In the last class, we were discussing about implicit method. To solve 1D unsteady state heat conduction problem. So in that case, we came to know that the set of equations form a tridiagonal matrix with variables, maybe x1, x2, xn. R1, R2, Rn. So to solve these kind of matrices where we have diagonal elements and all other elements 0, to take an advantage of such a structure, to solve a, we can use direct methods, direct method. For example, Gauss elimination. But if you see here, since there are 0 elements present here, and if we use Gauss elimination, unnecessarily there may be a problem happen that in order to reduce this, remove these values, we may get some values here. Okay, so we may not possibly get the all zeros here, and all somewhere you may get some other value. Okay, so that may be very cumbersome, and also number of operations in Gauss eliminations could be very high. Okay. However, for such a banded matrix, banded matrix, Gauss elimination Gauss elimination is very costly. Therefore, to take an advantage of tridiagonal nature of the matrix a special algorithm that is variant of Gauss elimination only, or you can say LU type. L lower and U upper. Okay. Is given by Thomas which is now called as Thomas algorithm, or tridiagonal matrix algorithm. Okay.
Sir,
Yes.
sir, what do you mean by actually banded matrix? Sir?
This is a band. This type of matrix are called as banded, having some structure.
Okay.
So this is called as banded matrix. You have a band. You have this upper diagonal, this lower diagonal, and diagonal. Other method is the iterative methods. Okay, so all iterative methods you can use. The most popular iterative method is Gauss-Seidel, and we have seen. Okay, Gauss-Seidel method we already seen. Now, in such cases, if the matrix is banded and of small size, if the matrix is banded and of small size, then it is wise to use TDMA over Gauss-Seidel. However, in more general case, Like in softwares, like Fluent software, all use implicit Gauss-Seidel method. Or we call line by line Gauss-Seidel method.
Sir,
Excuse me. Hmm.
sir, in the exam, we can use any method you want, or it will be mentioned specifically to use that method
If it
for
is
solving.
mentioned, you will have to use that. If it is
Else,
not, then you are free.
okay.
Okay. So we're looking at the TDMA algorithm. So already I have given two steps of TDMA, that is the reduction to upper triangular form and the back substitution. Now today we'll see the algorithm to use this TDMA algorithm on computers. So first thing first you have to do is you have to initialize all your variables. Okay, initialize. So say length, time, all the parameters you have. Okay, and then you may be having this old temperature values, then you may be having this new temperature values. You will have to use some variable. Okay, you cannot use variable like this t to the power n. So this is a some pseudo code. I'm writing this a for above and b for below diagonal elements, and d for diagonal elements. Okay, so you will have to specify what are the you will have to store these elements, these green elements in a matrix a array, and this red one in d array, and this blue one in a b array. Okay, similarly you will need an array for your right hand side terms. For solution variable you will need, that is nothing but your t only, and you might need dx means delta x, you might need delta x, delta t, alpha, gamma. You cannot use alpha symbol. Huh? You will have to write ALPHA if you are using C program, A, H. Uh, since these are given values TL, T naught, and if you have a bio number also, you store that. The second thing is initial conditions. Okay, initial conditions. In this initialization, you might have some counters. You might use some counters, some counter or some variable, some other variable, where you need to give some zero value to that in the beginning, so that there is no random value present in that variable. So that initialization will take care of that. So no, in this all this, there won't be any random numbers available. This initial condition is our part of your problem. Whatever the initial condition is given, so for I equals to 1 to n, you can give t n I is equals to whatever the value, this is the initial value T naught, and then in right side, the solution, right side, you will have to specify not solution Ti. Okay, because all the times right hand side is a known value. Right hand side is a known value. Here, these will be known values, and these will be unknown values. Okay, and we are trying to find out unknowns. But known values, that is Tn, is already known, T naught, which will be some value. So we say that right hand side is Tn. Then we go for a, once this initialization is done, then we go for a time stepping. Okay. So it means that suppose this is our X domain, and with discretized domains, now we have given at t is equals to 0, we have substituted values at all these points. We have assigned values to all these points, and these values are nothing but T naught, T naught, T naught, T naught. By doing this, we have done this. Now, by time stepping, we move into time, so that we go for next time, and we do calculate here. Now here this is a boundary node, this is a boundary node, so these values will have to force by you, and this will be calculated. Okay. In another time, then again you will go next time with some delta t. Stepping has to be done with some delta t's. You cannot jump directly, so delta t should be such a way that we should not unnecessarily increase round of errors. Here there is no problem of stability, since this is an implicit algorithm. So again, we have a boundary condition here, we have boundary condition here, and we find the interior points values from the previous. Okay, at t is equals to 2. And then we keep on doing this, and we stop at a moment where t n plus or n plus 1 value and n value do not vary. Okay, we stop there. So now I start here. Time stepping started. So for L is equals to 1, 2, m, I'm calling a function. Whatever the Tdm algorithm is there, I am putting that in a function. Okay. Many times while writing a program, it is good to create a function which is doing a specific activity. So we are writing tridag, something like, so we call this and we give the values of n, and suppose BO number is also there, and it was there. Okay, in our case A, B, D, R, X, this you will have to give, and then after calling this, you will get some values, and then finally you have to do this. Okay. Now what is the component of this tridiagonal? I will give later on, but let me write this. Then for j is equals to 2, to n, you write like Tn plus 1. This is T new 1 is equals to TL and x1 is equals to Tn plus 1 1. Okay, x is a T only, but x is a temperature only. But here we are using different variables, so I am first storing TL, which is a known value at the boundary, in a variable, and that variable I am storing in another variable x. So in that sense, Tn plus 1 j is equals to xj. And then for use another for loop for I is equals to 1 to n, you use Tn I, okay, not 1, Tn I is equals to Tn plus 1 I. This is needed, okay, because when you want to calculate this one, when you want to calculate these one values, these are n plus 1 and these are nth. Okay, these are nth level values. And these are n plus 1, n plus 1th level values. But when you are at t is equals to 2, when you are at t is equals to 2, these are n plus 1 values and these are nth values. So what you have to do is you have to assign this. Whatever value you obtained, you have to assign yes here. Okay. This is what is done here. This is what done here. Then only we can move into time. Okay. So for t is equals to 2, you will be calculating Tn plus 1 with known values. Unknown values become now known. Similarly, when you go for t is equals to 3, these unknown values will be known, and t is equals to whatever t is equals to 3 values are there, they will be unknown. Okay. Then next step is the fourth step. Fourth step is you have to say from T0 you are moving to T1, or from T1 you are moving to T2, or from T2 you are moving to next. So n is a time variable, n plus 1. And if you have t, then you can write t plus delta t. So next delta t will be used in that. Tn will be equals to Tn plus 1. Okay. For I is equals to 1 to n. This you have to do, okay? Because finally, if you found that there is no variation between 2 and 1, t is equals to 2 and t is equals to 1, okay? Or you say t is equals to large value and just before that value, if there is no variation, you have to say that these values are now known values. So that is the reason we are mentioning that Tn, and we are printing these values, Tn only. So for here, then once this is done, then go back to step number 3. Go back to 3 till stopping criteria is met. Stopping criteria can be given as magnitude of Tn plus 1 minus Tn at all I. These are all I. should be less than, say, small number 10 to the power minus 5. Okay, so this is very simple. Okay, now what is important is how do we calculate the solution? This is after getting a solution. So once you initialize, you got the solution, and you are just uh, assigning that solution to proper variables and printing those variables, and then again you are moving in the next time step so that you get this switch, you put it in the tridag, and then again get the solution. But how do you get the solution? So that I will write as a subroutine here. So that subroutine. Subroutine is also called as function. Sorry, not routine. This is also called as function in C, and subroutine is general word used in Fortran. Okay, generally used in Fortran. And function is the word generally used in C or C++, and in most of the variants programming languages. So subroutine triadiag.
Hello, sir.
Yes.
Sir, this subroutine tridag will be a user-defined function, or it's already defined in the compiler.
No, you will have to define. That is what we are defining here.
Okay, okay.
Okay. This
Okay.
is uh, a calling function. Okay. Here we are calling a function and we are defining a function here. Okay. So this will be created by you. This function will be written by you. So you have to write like integer n, float, whatever the values you have given here, they should be in that n. What is the type of the n? What is the type of the BO number? So float BO, then float gamma, or you can write real or float A array, float B, B, float D, float R, float X. Okay, close it. And then here in this function, all what we are doing is we are writing all pseudocode. Okay, so in this initialize again, initialize, what you have to initialize? N, Bi, gamma, A, B, D, R, X. And then second, assign the values. Okay, assign the values. We want to assign values to this A, B, D, but before you create these arrays, it is better to initialize them with some 0 values. Okay, assign the, and then next you assign the values. So I'm assigning the values now. So A1, what is my A1 in the matrix? That you have to assign. So we have seen that A1 is 0 in our case. Okay, we already solved that problem and we obtained a matrix, right? That 1D unsteady heat conduction problem. There we got the proper with gamma and all this, we got certain terms. So A1 is 0, then D 1, you will have to store all the values. Huh? If this is the matrix and these values are there, you have to store these values. Okay, are you getting this? So this is A value, this is D value, and this is B values. All these values you have to specify. So D1, you say D1, what is your D1? You say 1. Then what is your B1? You give all the values of the elements. Okay, so assign the values of the elements of matrix, of the elements of matrix. Okay, so by this, what does it mean? You should know what is a matrix you are getting, or what are the elements, or what are the numbers in the matrix. Okay, so it is not general in that sense. It is not so general in that sense that you have a random matrix and then just storing these values. You will have to intentionally specify these values. Okay, so that is also one of the reason it is not so general, not so used in a generalized codes. So B1 is your minus gamma. Similarly, Dn is your 1 plus BO, 1 by BO. Bn is your minus 1 by BO. Ri is equals to TL Rn. So everything, okay, everything you have to specify. All the values needed, that has to be specified. Then once you assign these values, the next step is to start from, for I is equals to 2 to n, assign again the values. Not means these are the initial first values and last values. Okay, assign the values. Interior points. Interior points have a certain pattern, isn't it? So assign the values. So I is equals to 2 to n, and you are doing this activity, n minus 1. Assign the values of ai is equals to gamma. This is fixed. Di's, you will see mostly they are of this nature, 1 plus 2 gamma, and all bi's till n minus 1, they are also they were also gamma or negative gamma? Negative gamma, isn't it? They were negative gamma. Negative this left side, negative right side, and then positive central coefficient is positive. Okay, so we have now, by doing this, what we have done is we have specified with this 2 and 3. With this 2 and 3, we have specified all these values. Okay, now matrix is known. Okay, all the elements of the matrix are known in this. Now, once we know all the elements, next step is to do elimination. This is called as forward elimination. Forward elimination. Okay, Now in forward elimination, we go from for I is equals to 2 to n, last term. First term is a boundary condition, so we leave that. And it's a known. So, and last term is a derivative term, so it's not known, so we go from 2 to n. Then for this, do this thing, di, calculate the central, diagonal element d. Di is equals to di minus bi multiplied by a I minus 1 divided by di minus 1. Okay. So by this you will get all d's, changed diagonal, new diagonal elements. Okay. So by doing this process, what do we do is by doing this process, elimination process, we convert this matrix into a upper triangular matrix where these elements, so since I have taken 2, these remain same, but these are getting modified. These are modified. And the rest got eliminated. And the rest got eliminated. So these will be eliminated. These will be eliminated. And these will be modified. Okay. These will be modified. So DIs are now getting modified here with this formula, and this is a fixed formula, known formula, and given by the Thomas. Okay. And you can prove this formula by doing that Gauss elimination process, a very special case of Gauss elimination, and you can prove this formula. And then you calculate the right hand variable. Similarly, here you have this. So here also you have in the right hand side, you have some variables. These also will get modified. Okay. These also will get modified. So Ri will be equals to Ri minus Vi into Ri minus 1 divided by Di minus 1. Okay. So we got the new modified values of the elements of the matrix and the right hand side values. Okay. These will be the new values. We got this. Okay.
Sir, in this
Yeah.
formula, it's a PI or AI, sir.
Hmm?
In this formula, Ri is equal to Ri minus BI.
BI
In
is
that,
there. Yes.
BI or AI is come there.
No, BI. Like this, you see here, BI, you do that elimination thing. Okay. If you do that elimination thing, you will come to that. This is the formula. So BI is there. In the previous class also, we have written like that, isn't it? This is the fourth step. Huh? Okay. So you get all DIs and all RIs, new values of the RIs. And then what do you do? Once you get these new values, it means that you got this type of form. You got your form. And this is the needed form. This is the needed form. Now, you know this, suppose this is xn variable. Now simply this multiplied by xn, this value multiplied by xn is equals to the right hand side value. So xn will be equals to the right hand side value divided by this x. Okay. So we do for this first, we do the back substitution that way. And for second case, then this value is known value. This is unknown. So we substitute in a different manner. So next step is 5, that is called as back substitution, backward substitution, backward substitution. The student who have asked me a question, please note that in one lecture, it depends upon this notation. Okay, now we are using this notation D for diagonal, A for above, okay, and B for below. Okay, in some case I might have used A here, so don't get confused with that.
Okay, sir.
In some case, maybe in our previous lecture, I might have used like this: A, B, 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 and C might be there. Okay, so don't get confused. So don't get confused. Now we are talking with respect to this. D means diagonal, A means above diagonal, and B means below diagonal. Okay, so let me write here so that confusion will not be there. Note D means diagonal elements. B means below diagonal elements. And A means above diagonal elements. So whatever I'm discussing now, I'm discussing with respect to whatever the notation I have given in the last class. Okay, Tuesday's class, not that Saturday class. Some Saturday class I have given a different form of the matrix, but tri-diagonal only, but different notations. So if you are looking in that sense, so you will, I think that is the reason you are making that question. So in the back substitution, this last term is simply simply xn is equals to whatever the rn value is there, rn, this value divided by the diagonal value, isn't it? This is a diagonal value. This is a diagonal value, dn. And this is the last value, so n value, capital N value. And this is the last r value, so rn. Rn divided by dn is this. Then from the t for x n minus 1 to x1, we have to write separately for I is equals to n minus 1 to 1. Okay, xi will be equals to ri divided by di, ri divided by di minus ai into x I plus 1 divided by di. And also, if I remember in the last class, by mistake I written for Ri this values, this formula. Okay, so then I later on changed it. So if you're disconnected afterward, you please correct it. Okay, I corrected it later. Okay. Well, writing I just was writing in that sense. So you please note, in your back substitution only you have AI. In forward elimination you have BI and DIs and corresponding A and R. And here corresponding X and D and AI and RI and DI. Okay. So this way you have to calculate. So by this you know everything. D, R, you know, and once you know D's and R's, you can calculate X's. So X's are nothing but temperatures values. So once this function is called, all X values are calculated, and these X values, these X values, these X values, then these X values are substituted here. Okay. And these values again substitute as Tn. So it is like some arrangement. Okay. This is some arrangement in order to assign these values to these values. Okay. So this is suppose t is equals to n and t is equals to n plus 1. So finally, we assign these n plus 1 values as a n level values. Okay. And then again we keep on calculating. So for next time, we'll calculate again xi's, all x values, means temperature values. It's just different variables used and then exchange of the information in corresponding variables. So you work on this algorithm, okay? Because your assignment is to write one explicit code and one this implicit method, specifically tridiagonal matrix algorithm. And it is very simple, but since you will have to work on it, because if you start writing a program, you may face some errors, some this thing, but finally you should be in a position to do it. Huh? Okay, now I'll just make a general comment. Now what we have done is, for solving this type of problems, del t is equals to alpha del 2t del x2, we had used one explicit method, isn't it? Explicit method, and also we said that there are the implicit methods. Now, one explicit method we have discussed, that is called as forward in time and central in space. Implicit method we have discussed, that is called as backward in time and central in space. But are these only the explicit and implicit methods? Are these only explicit and implicit methods? It appears that no, isn't it? It is possible to make it FT or maybe some other, different system. Okay. So maybe central CTCS, central in time and central in space. Likewise, so there is a possibility that there can be variants of other methods available. Okay. So one method in this explicit category, one method is called as Richardson method. Richardson method. Okay. Now in Richardson method, what is done is this time derivative is taken like this: Ti minus Ti, isn't it? And divided by twice delta T. So you can understand when it is taken as twice delta T, this is n plus 1 and n plus 2. So twice delta T means if this is the central value n, so n plus 1 and n minus 1, if this is the n, then n plus 1 and n minus 1 is coming into picture. So this is n plus 1 and n minus 1. Okay. So time derivative is taken like this: n plus 1 and n. Evaluated at n. And the other discrete parts, they are taken as Ti minus 1 minus twice Ti plus Ti plus 1 delta x square. And what should be here? What should be on the top? What are these values? Are these known or unknown values? These are all known values because we are talking about explicit, and in explicit method there is only one unknown. Here n plus 1, this is also known, n, this is also known, n, this is also known. Okay, if this is the nth level value, known value, means before that all are known values only, isn't it? This is a known value, means all are known values in time. But the n plus 1 is unknown. This is unknown. This is unknown. But n and below that all are known. These all are known values. Okay. Hope you understand. So this is central in time and central in space, isn't it? CTCS. This is a central in time and central in space. This is called as Richardson method. CTCS is a Richardson method. You can use this method also and you can find out the Ti n plus 1. Okay. So in the exams you may be asked to do with this, or you may be asked to do with this, or if it is not specified, you are free to use any method. Okay. Other possibility in the explicit category is called as Dufort-Frankel method. Dufort-Frankel method. Frankel method. If you get a good command on one method, that is enough, because you can also, they are on same line, only some part of the difference is there. So now in Dufort-Frankel method, what is done is the time derivative that remains as central in time, Ti n plus 1 n minus 1 divided by twice delta T, and a small change is made in the right hand side. Okay, so here Ti minus 1 and minus 2 here ij term is used as a average of n plus 1 and ti plus ti n plus 1 and n minus 1 plus ti plus 1 divided by delta x square. Okay, this is how it is done. So here, if you see, is this explicit or implicit? Now you see there is one n plus 1, isn't it? There is another n plus 1. So how many unknowns are there? How many unknowns are there? How many unknowns? Anybody?
2, sir.
So one unknown only, sir.
One unknown only. Yes, one unknown only. Because it is the same unknown, isn't it? One unknown only. So it is explicit. Okay, don't get confused. If it is, it would have been like I plus 1 or I minus 1, and then it is problem. Since it is I, this is explicitly solvable. Okay. Now this method, Richardson method, is having a truncation error of the order of delta x squared and delta t square, because all central difference. Here the truncation error, you will have to prove this. Okay, you should be knowing this, and you should be in a position to prove using Taylor series. It may be asked in the exams. T is order of delta t square, delta x square, whole square, huh? And you also have delta t by delta x square. Okay, truncation error is of order this, 2-fold Frankel. You see there is a problem here, consistency may be a problem. So I think 3 methods are enough. There can be a lot of method you can get, if you look in the literature, you will get a lot of methods. Okay. So rather than going in too many methods, it is better to go in one method and understand first, and then later on you can. But sometimes when you finish a course, some people, they think that, oh, this method is not taken, that method is not taken. Everything cannot be taken in a small course. So one thing is, first you master a simple one, and then you can extend that mastery to other methods. And they are just same, you should only know how they are doing. Then you combine this and you get finally a explicit version of this, isn't it? This is nothing but you have to combine this, you have to bring this Ti left side. It will be one unknown and all other knowns. Okay, now in the implicit category, very popularly, yeah, time is over.
Yes, sir, we have max class, sir.
Yes, please. Yeah,
Okay.
okay.